So recall that if p of x is an irreducible polynomial, so p is a polynomial over field f, so you can form a field like this where alpha is the root of this polynomial. It is irreducible polynomial. So this would immediately imply that f alpha over f, this degree of extension here, is precisely the degree of the irreducible polynomial. So this we have seen before. So for example, you attach 2 1 by 4 to rationals. Over rationals, this is 4, where the minimal polynomial is x4 minus 2 over rationals. Similarly, attach this I, this complex number. So this I is square root of minus 1. So attach this to rationals. So this qi over rationals is 2. Your minimal polynomial is x square plus 1. Now we can extend this further. So you can say that this rationals, your joint 2 1 4 and I to it over rationals 2 1 by 4 is again 2, because your minimal polynomial is x square plus 1, which lies over rationals 2 1 by 4. So you still have to show that this polynomial is irreducible over this field, and this is easy to show because you know the root of this polynomial is this complex number I, which does not lie in rationals your joint 2 1 by 4 to it, because this is just real. This is just a subfield of real numbers, whereas this is a complex number here. So now you can compute this rationals your joint 2 1 by 4 and complex number to it over rationals. You can write it like this and then like this, so these two will cancel out, but this you have computed to be 4 right here. So this is 4 right here, so you get this as 4, and this portion is 2 right here, so this portion is 2, so you get 2 times 4 is 8. So adjoining 2 1 4 and a complex number I to rationals and then over rationals will give you 8. So notice that we had to proceed step by step. So at every step we had to consider an irreducible polynomial. So first step you consider irreducible polynomial here, and this was the second step, and you consider irreducible polynomial here. So notice that the splitting field for x4 minus 2 over these rationals is this, because you know this splits completely like this: x minus 2 1 by 4, then plus 2 1 by 4, this and this. So obviously you first split it as x square minus root 2 times, then you have x square plus root 2 here, which further splits like this. This you can see. So this is the splitting field because you have done nothing much. You have just adjoined the roots 2 1 by 4 and the complex number I. So therefore this this extension adjoining 2 1 by 4 and complex I to rationals over rationals is a Galois extension, precisely because you have been able to find a polynomial x4 minus 2 over rationals which is separable. So since you have been able to find a separable polynomial, separable means it has distinct roots, this is a Galois extension. Now the automorphisms of this extension, or the Galois group corresponding to this, is D8, the dihedral group. So ideally we would like it to be S4, that is, you know, there are 4 roots, we should be able to permute it, and this group will have the order of this group is 24. So this is too big. Instead we have a much smaller group which is of order 8. That is because the generators here interact with each other. So this is not the Galois group for this extension. So the two generators are sigma and tau. Obviously these two generators correspond to two irreducible equations. So sigma acts on the roots of x4 minus 2. It will try sending the roots 2 1 by 4 to 2 1 by 4 minus 2 1 by 4, this complex and this minus I complex. So this is where it tries to send it. This is corresponding to this. And tau is corresponding to our equation x square plus 1. So notice that while computing this 8 we had two equations, x square plus 1 and x square minus 4, and that's how you got 4 times 2 8. So tau sends this complex I to complex I and then minus complex I. So again the sigma and tau interact with each other, and we will in fact show that you will get a dihedral group which looks like this. It is generated by sigma and tau, where sigma 4 would be 1, tau square would be 1, and this tau sigma will be equal to sigma cube of tau. So sigma will just act on the roots of x4 minus 2. So sigma will just act on 2 1 by 4. And it will not touch this complex I, which is the root of x square plus 1. So sigma keeps I as such, and 2 1 by 4, it multiplies 2 1 by 4 by complex I. So sigma square means you take sigma and apply this sigma to it. So this is I 2 1 by 4, multiply with complex I, you get negative 2 1 by 4. Sigma cube, you take sigma square, apply sigma to it, that is multiply what you have here by I, you get negative I 2 1 by 4. Sigma 4 now, you apply, take this, then apply sigma to it, that is multiply by I, you get minus I square 2 1 by 4, which is 2 1 by 4, which is just identity. So sigma 4 will just give you our identity. And this sigma is not having any impact on these complex I. So notice how sigma is permuting the roots. So first action is 2 1 by 4 goes to I 2 1 by 4, and then it goes to minus 2 1 by 4, then it goes to minus I 2 1 by 4, and then it ends up at 2 1 by 4. So all the roots are being permuted by sigma. Similarly, tau permutes the root of this polynomial. So it takes this complex I to negative I, and it has no impact on 2 1 by 4. But now we should see how these two are interacting, sigma and tau. So let us take sigma tau. So this tau will have no impact on 2 1 by 4. Only sigma is going to have an impact on it. So the entire impact comes from here. So this you copy here. Similarly, sigma square tau here, tau will have no impact on 2 1 by 4. Whereas sigma square will act on this to give you this. So you have precisely this result here. Again, sigma cube tau, tau will have no impact here. Sigma cube will act on this to give you minus I to 1 by 4, which comes right here. On the other hand, tau permutes I to negative I, puts it right here. Again, tau will take this I to negative I, but sigma will have no impact on this, so negative I. Similarly here, tau will take this I to negative I, but sigma square will have no impact on it, because it just impacts this root right here. It does not impact I. Similarly here, sigma cube tau will have only take this I to negative I corresponding to tau. So what about other permutations? What about tau sigma? So you can do tau sigma also. First apply sigma and then apply tau, but you will get precisely this result. Similarly here, you can apply tau sigma square. So first apply sigma square and then you apply tau to it. You will still get the same column like this. And then you get, say, tau sigma cube. Then you get this column. So we here took just sigma tau, sigma square tau, sigma cube tau, but you could have said that, I want to take tau first and start with tau sigma. Then you would have get precisely this thing, and this thing. So you can see all the options, and these are the only options you get. And now you can count the number of elements. There are precisely 8 elements. So 4 are here and then 4 are here. So you have 8 elements. And this is the dihedral group. Sigma 4 is identity, tau square is identity, and this tau sigma is equal to sigma cube tau. You can see this. So this is also, these two are equal to each other. So we do have a dihedral group. So now we have our big group G, which acts on this automorphism. So this big group G is the automorphism here. So we have computed our Galois group corresponding to our Galois extension. So we have the big group G, the Galois group, but now we want to talk about its subgroups. So this we have seen that this big group has order 8. You can write it as dihedral group, dihedral group. So the groups of order 4. So first group is 1, sigma, sigma square, and sigma cube. So this group here, sigma 4 is identity generated just by sigma. So this is just cyclic group of order 4. Then you can see the group generated by sigma square and tau. So sigma square tau, again this is z2 times z2, because order of sigma square is again identity, sigma 4 is identity as we have seen, and tau square is also identity. So this is true. Again here you can consider another group of order 4 which is generated by sigma square and sigma tau. So you multiply these to get sigma cube of tau, but again you know that sigma square order of this is just 1, and sigma tau square is also 1. So see sigma tau and then you have sigma tau. So now you see this tau sigma is precisely the sigma cube tau. So you can rewrite this as sigma. So instead of this, we are writing sigma cube tau and tau. But these two now become identity. Tau square is identity, and the sigma 4 is identity. So again, you get identity. So group of order 2 generated by 1 and sigma square. Again, sigma 4 is identity. 1 and tau. 1 and sigma tau. Again, all these are cyclic groups of order 2. So again, we have already checked this as identity. Again, sigma square tau. You can check sigma square tau. This is identity. Sigma cube tau. This is identity. So we have a couple of groups of order 2, and then we have the corresponding group of order 1, which is just the identity map. Now we talk about the Galois correspondence. So we have fields here and we have groups here. So obviously the identity map will fix the entire splitting field, whereas we have seen the dihedral group will permute both of these roots. So this is the dihedral group D8, and you see that it permutes I ascend to minus I, and it also permutes 2 1 by 4. So the dihedral group only fixes our rationals right here, and identity map fixes this. Now look at tau. So the tau, it permutes I, this complex number it sends to minus I, whereas it keeps 2 1 by 4 fixed. So this tau is 2 1 by 4, it is fixed. So corresponding to subgroup generated by tau, this is fixed. So this subgroup is precisely this group we are talking about, this group here. So instead of this entire group 1 comma tau, we are just writing the generator. So there is a correspondence here and here. Again, look at group generated by sigma, this group. This is just permuting 2 1 by 4. It is taking it to all 4 roots, but it is keeping this complex I fixed. So sigma is keeping this I fixed. So you can see the correspondence between this and this right here, here and here. So again, you can see correspondence between sigma square tau and rationals root 2. So tau will obviously permute complex I. So you do not have I here. So I is obviously not fixed. What about sigma square tau? So sigma square tau will fix root 2. So the way to see this is like this. So sigma square tau of root 2, you rewrite this as sigma square tau of, instead of root 2 you write 2 to the power of 1 by 4 times 2 to the power of 1 by 4, and obviously now you use the multiplicative property of homomorphism. You write it at 2 to the power of 1 by 4 times sigma square tau 2 to the power of 1 by 4. Again, this gets mapped to, so sigma square tau acting on 2 1 by 4 gets mapped to negative 2 1 by 4. So this becomes negative 2 1 by 4. This is also negative 2 1 by 4. So times negative 2 1 by 4. Again you get root 2. So you see root 2 is fixed. Nothing else is fixed. You can see 2 1 by 4 is mapped to I 2 1 by 4. This I is mapped to minus I. So this is the fixed field is root 2 right here. Similarly, you can see sigma square and sigma tau. They will fix this complex I root 2. So you have to check for both the generators. So you can see sigma square of I root 2. You rewrite it like this. Sigma square of this I times sigma square of, instead of root 2 we are writing 2 1 by 4 times 2 1 by 4. So again, sigma square of I would remain as such, because sigma square of I is as such. 2 1 by 4 and 2 1 by 4 is sent to negative 2 1 by 4. So this will be negative 2 1 by 4 times again negative 2 to the power of 1 by 4, which will again give you I root 2. Similarly, you can check with sigma tau that this will be fixed. So you can see the correspondence between here and here, and you can see most correspondence like this. So for sigma square, again you can see sigma square fixes I. So sigma square acts on I, fixes I. So corresponding to sigma square, you have that the I is fixed. But again it sends 2 1 by 4 to negative 2 1 by 4, and just by a similar procedure here you can show that it will fix root 2. So for most of the groups we can show like this, but there is some complication which arises when we have to show how do we associate these groups to this correspondence. So now we will show in detail how to associate the group generated by sigma tau to rationals 1 plus complex I times 2 1 by 4. So notice that sigma tau is right here. Sigma tau sends 2 1 by 4 to I 2 1 by 4, and it sends I to negative I. So we want to show this Galois correspondence, that the subgroup generated by sigma tau, it fixes this field right here. So recall what sigma tau does. So sigma tau sends this 2 1 4 to I 2 1 4. I is this complex number, and then this I to minus I. So again, recall this I is nothing but square root of minus 1. So we want to now talk about the elements of the splitting field, this field, over rationals. And this has degree 8. But it is generated by two elements, this complex number I and 2 1 4. So notice that this 2 1 4, this comes from our polynomial x4 minus 2. And obviously this comes from the polynomial x square plus 1. So we can only go to the power of 3 here. So the element looks like this: C0, C1, 2 1 4, then 2 2 4, 2 3 4. After that we have to start adjoining this I. So you have I, then I, again 2 1 4, same as here, 2 2 4 here, and then 2 3 4 here. So again you can count, there are 8 elements here. So you're going from 0 to 7, so you have 8 elements here. But this 2 1 4 just goes all the way to 2 3 4 because it is coming from here, and then identity which is 2 4 by 4. So we are saying that elements of this field which are fixed. So what are the elements which are fixed here? So we have to prove those elements are precisely of this form, but that would mean that sigma tau would fix x. So let us see first the action of sigma tau on x. So all these CIs are rational because we are talking about the splitting field over rationals. So CI are rational. So these rationals are going to be fixed by sigma tau anyway. So C0 fixes to C0, C1 goes to C1, but 2 1 by 4 you can see here goes here. Then 2 2 by 4. So multiplicative property of homomorphisms come into play. So sigma tau, so you take square here, you will get a square here. So that's what we do. You take this here and this square comes out. 2 3 by 4, again you take 2 1 by 4 inside as like this, I 2 1 by 4, and then this power 3 comes out. Now sigma tau acting on this complex I gives you negative I. So this I goes to negative I here. Again this I goes to negative I here, but 2 1 by 4 now goes to I 2 1 by 4. Because sigma tau is acting on it. So say you first act on I and then you act on 2 1 by 4. Again the multiplicative property like this. Again this I will go to negative I, and this 2 to the power of 2 by 4 will go to I 2 1 by 4 square. This is exactly the same thing what we have done right here. Similarly for I 2 3 by 4, so I will go to negative I, and this 2 3 by 4 will go to I 2 1 by 4 cubed. Precisely what we have done here. So now you can start expanding. C0 just remains C0. So we are trying to find the basis first: 2 1 by 4, 2 2 by 4, 2 3 by 4. So 2 1 by 4 precisely comes from C5 here. So notice that what we are using is I square is negative 1, and we are also using I cube is negative I, and that's all we are using. So you get negative I square, which is 1, you get here. Then you see C2, I square will give you negative. You have this 2 2 by 4, and 2 3 by 4 you have C7. Again you have negative I square, which will give you negative C7. Then you have C4, which is just negative C4I. C1, you just copying this right here. C6, this thing right here, you have I square times negative I cubed. So negative I cubed is just I. That's what you get here. Right here, 2 2 by 4, and then finally C3, just I cube is again negative I, so you get negative I, negative comes out, you get this. So we are saying that when will sigma tau fix x? So if you act on x, this is what you get. So to fix x, this should be equal to this. So x should be equal to sigma tau x. So for that, all the coefficients should agree because we have made sure the bases are the same. So these bases are the same: 2 3 by 4, 2 3 by 4, I 2 1 by 4, I 2 1 by 4. Again, the base is the same, basis is the same. So to do this, we have to equate the coefficients. So if you want to fix the elements, the coefficients should be fixed. So C0, C0. You have C1 has to be equal to C5, so C0 is C0, C1 has to be equal to C5, C2 has to be equal to negative C2, C2 is negative C2, C3 has to be equal to negative C7, C3 is negative C7, C4 has to be equal to negative C4, C4 negative C4, then C5 has to be equal to C1, C5 has to be equal to C1, C6 has to be equal to C6, C7 has to be equal to negative C3, and that's it. So now you can see that C0 and C6 are arbitrary. So it doesn't matter what you do, C0 will always come equal to C0 here, and similarly C6 will come equal to C6. So you can put any values here. On the other hand, if you try to solve this, you get 2C2 equals to 0 if you try to solve this equation. So this implies C2 is just 0. Similarly, C4 equals to negative C4 implies 2C4 is 0. So C4 would also be 0. So this you can solve to be 0. So C1 equals to C5, this you have, and then you have this equation. C3 equals to negative C7, and again C3 equals to negative C7 from here. So this we are copying right here. So now you make these changes in this equation right above here. So once you make these changes, this is what you will get. C0 comes as such. You set C1 equals to C5. So this you set equal to C1. And then you have C1 right here. You get 1 plus I 2 to the 1 by 4. Then you have C6, which is just arbitrary, so comes as such. So C6 you don't do anything, just copy it as such right here. For C3, you keep C3 here and set C7 equals to minus C3, and then you will get 1 minus I 2 3 by 4. So this will become positive obviously, because instead of C7 you're writing minus C3. So this is what you get. But this you can rewrite. Don't make any changes here, don't make any changes here. Here you know that 1 plus I square, this will give you just 2I. So instead of I, you write 2I, divide by 2 and write 1 plus I square. Similarly, you can write, instead of 1 minus I, you can write 1 plus I cubed, which will be equal to 1 plus I square times 1 plus I, which in turn is, you can see here, 2I times 1 plus I, and then you just get 2I minus 2. And then again you can take 2 common out, put a negative sign so that it becomes I minus 1, divide by 2, put a cube here, this. But the idea is, now see, the basis is this, then basis is square of this, then the basis is cube of this. So these three lie obviously in Q or joined with this. So because this is the basis, you are saying first basis square cubed. So this is the basis. So we have shown that sigma tau is a subgroup which fixes this field. So notice that we have actually constructed everything, or shown that sigma tau is precisely going to fix elements which look like this. So there is a lot of work to be done to show the Galois correspondence between the subgroup and the corresponding. So the subgroups marked in green are the only normal subgroups of D8. Obviously identity is always a normal subgroup, but these are the normal subgroups in D8. So the extensions corresponding to these subgroups are precisely the ones which are Galois. So if H is a normal subgroup of G, if and only if KH over F is Galois. So these extensions which correspond to these green subgroups are Galois. And obviously then this will hold. So D8 has order 8 and sigma square tau. So see, this sigma square and tau is right here. Sigma square and tau, this is order 4. So this is order 8. So you expect this extension to be 2 because g over h is 2. Again sigma has order 4. You expect this to be 2. Then sigma square sigma tau, this is also normal subgroup. So notice that all these subgroups are normal subgroups, all of them. So this is also of order 4, so this is 2. So again you have the sigma square, this is a normal subgroup, this is actually a normal subgroup here and a normal subgroup here, so this is 2. So overall extension on D8 is 4. So 8 divided by 2 will give you 4 overall, 2 times 2. If you just want to consider it as a normal subgroup of sigma, then it is just 2. So this is what we get, because once you modulo out you also get factor groups. So corresponding extensions here should have the same degree as here, which is suggested by this result. So automorphisms of kh which fix f. So here kh is rationals root 2 and f is rationals. Here kh is rationals adjoint complex I and f is rationals. Here kh is rationals adjoint with I times root 2 and f is again rationals. So see what are the corresponding polynomials. So here the polynomial is x square minus 2. So degree is 2. Here the polynomial is x square plus 1. So the degree is again 2. Here the polynomial is x square plus 2. So degree of the polynomial is 2. So this extension is also 2. Here again the polynomial here is x square minus 2. So we have to again show here, once you write this, that x square minus 2 is irreducible over a rationals adjoint complex number, simply because even if you adjoint complex number to rationals, it still does not contain square root of 2. So you have 2 here. So you can see all these 2's match 2's here. You could also consider this directly, this here q I root 2, you can see this directly over q also. In that case you consider this polynomial which is a product of these two polynomials, which would be x4 minus x square minus 2. Notice that this is not irreducible, it is product of two polynomials, but that does not matter, it is still Galois and degree is 4. Piece by piece you can consider 2 here, 2 here. Now these other extensions will also have degrees attached to them. So other extensions have degrees attached to them. So all these extensions have degrees attached to them, but they are not Galois. So notice that this q2 1 by 4 comma I, this is also Galois over q, because 1 is obviously a normal subgroup of D8. So notice that we are always talking about Galois extensions with respect to this. So this qi 2 1 by 4 is not Galois over rationals. Now you can see this, that using this equation, k over f is Galois if and only if k is splitting field for some separable polynomial. So if you have to adjoin this, then you have to use this polynomial x4 plus 2, but you see the other roots are not in here, so this extension is not Galois. So this extension over q is not Galois, this over q is not Galois. So again we are always talking about in reference to subgroups of D8 only. So notice that if you just talk about, say, these two fields in isolation, is qi 2 1 by 4 Galois over q root 2? So in this case you can just give some polynomial like this, say x square plus root 2. Then obviously you see that this polynomial will split like this: x minus I 2 to the power of 1 by 4 times x plus I 2 to the power of 1 by 4. Now you can clearly see that this splits completely over here, and this polynomial you can say lies in here over rationals root 2. So this extension just by itself is Galois, but notice that you cannot say the same thing about rationals here, because this x square plus root 2 does not lie in this rationals. It does not lie here because root 2 is not part of rational numbers. So if you try considering the small pieces, there could be Galois in between them, but we are always considering in reference to D8. So this is a big point of confusion. Similarly, since this is an identity map here, this identity map is obviously normal in all these groups. So you can say that, if you just consider these extensions by themselves, from going from here to here, 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 you can all construct them as normal extensions because you have identity map here. But we are not talking about these extensions. We are talking about whether you have kh over f is Galois, where f is your rational. So your base field is fixed to be rational numbers. So your reference point is this. So this is a reference point, not something in between. So now we know which extensions are Galois. So this is Galois, this is Galois, this is Galois, this is Galois, and this one is Galois. Others are not Galois.